All right, ladies and gentlemen, today's class recording has begun. So, if you don't want anything stupid to end up on the internet, don't say anything stupid. All right? Over the past couple weeks, we have been doing our introductory unit on mechanics. And we said when we're talking about mechanics, we're talking about describing motion. And we've talked about this like 1,000 times, right? Four things that we want to know. Four things that we want to know in order to accurately and descriptively, you can't descriptively describe something, I guess, but whatever. So, four things we want to know to accurately describe something. What are those four things? In order to describe the motion of an object. Jack, what's one thing?
What is the object doing now?
What is the object doing now, and what do we call that? There's two terms that we've used to sort of to describe what the object is doing now. You want some help?
Yeah.
What are the two terms that describe what an object is doing now, or could describe what an object is doing now? Nope. Nope. Velocity or speed, right? Depending on how detailed we want to be. So velocity or speed describe what an object is doing now. All right, what else do we want to know? Jack. Where is the object, right? So Jack, what's the term that we use to describe where an object is? Position, unless what happens? Unless it moves, then we would describe that movement in terms of distance or displacement, all right? So where is the object? That's position. What is it doing now? That's velocity. What's the third question that we want to know, or third thing we want to know about what an object is doing? Anybody else besides Jack? Not that we don't want Jack to dominate the conversation, but so. Timmy. What will the object be doing in the future when we call that what? What's the term that describes what the object is doing in the future? Acceleration. How much is the velocity changing, right? And then finally, the fourth thing that we want to know is where is it? What is it doing? What's it going to do next? And when, right? When are all these things happening? So the time frame that's involved. All right? Good there? Okay. To start off, on the first page, just to make some comparisons about where we're going here, we are going to start off talking about non-accelerated motion. What's another way of describing or naming non-accelerated motion? No, not negative acceleration. Eric. Constant what? Constant velocity, right? If something is non-accelerated, that means it has a constant velocity, right? So, how do we define velocity? What was our definition of velocity? How do we define velocity? What to delta x over? There we go. All right. So there's our definition of velocity, right? Velocity is a relationship between displacement and time. How far did we go versus how long it took us? Okay? So with that being said, here's a picture of a ball that's rolling along the floor at a constant velocity. Now, in real life this doesn't happen, and we'll talk more about that in the next chapter, but for now, let's say that it is, right? So, it says the ball rolls from the first position shown to the second position in 1 second. So I'm going to draw the ball right here, right? It says the two positions are 1 meter apart, just like in the picture. Okay? So that means if the ball went from here, position 1, to here, position 2, in 1 second, what is this ball's constant velocity? 1 meter per second, right? Because it took 1 second to go 1 meter. Okay, good there? And if it continues along at that constant velocity, how far will it go in the next second? Well, in the next second, it will only go 1 additional meter, right? So the third spot, right, would again be 1 meter after the second spot. Yes? Yeah. And then, right, the next second would be the fourth position of the ball. And then finally, even though I didn't really space them out correctly, right? Okay. In the fifth position, it would end up over there. Okay? Wait. Sorry, I messed up. That's why they're not spaced out properly. So that's why they're not spaced out properly. So all right. Here, here, here. Okay. Good there? Does that make sense?
Oh, yeah.
Sorry. The objector needs more detail.
Yeah.
Okay. All right. Good there? Does that make sense? 1, 2, 3, 4, 5 meters. Yep. Okay. We're all good. Okay. Now, here's what I'm going to do. Yeah, I'm not even going to do that. Okay. All right. Part A. Did you draw successive ball positions evenly spaced, further apart, or closer together? Evenly spaced, right? Why do we draw them evenly spaced? Constant velocity, right? And velocity tells us how far did it go and how long did it take it to go, right? So if each one of those ball positions represents 1 second, it should travel the same distance each time. All right? And that means when the ball reaches the wall, what is its speed going to be? 1 meter per second. We figured out from this interval right here that the ball's speed was 1 meter per second, right? Because it went 1 meter in 1 second. And that speed was constant, so we just keep going 1 meter each consecutive second, and that means if it started 5 meters away from the wall, how long is it going to take to get to the wall? 5 seconds. All right? Good there? Okay with that? So, in this case, here they use velocity, and here they use speed. Is it okay that at the beginning of this example they use velocity, and at the end of the example they use speed? Is that okay here? Yeah. In this example, yes, right? Because why? Same direction the entire time, right? If it had changed direction, if it had bounced off the wall or something like that, then we couldn't use those terms interchangeably. But here, that's fine. All right? Good there? All right. Directly underneath it on your sheet, right, we have a chart that I'm not going to go into too much detail because it's pretty straightforward, okay? So, we defined velocity before as displacement over time. Here, this table, I should do this. Here, this table has speed listed. How do we define or how do we calculate speed? Distance over time, right? And we said, Chris, just to review, like we said, distance and displacement are the same as long as we're doing what? Technically, yes, but that's not exactly the answer I was going for. Distance and displacement are the same as long as we're doing what, Olivia? As long as we go in the same direction, as long as we go in a straight line. As soon as we turn from that line, either left or right, or to go backwards, now distance and displacement aren't the same anymore. But as long as we're in the same line, distance and displacement are the same, okay? So, here's a chart that shows us distance, time, and speed, right? And Chris, like I said, speed is distance over time. So for the cheetah, right, if the cheetah travels 75 meters in 3 seconds, we take 75 as the distance, divided by 3 seconds as the time, and we get 25 meters per second, right? Good there? Okay. How about the greyhound? What is the greyhound's average speed? And hopefully this calculation isn't too difficult for you, right? 16 meters per second. Okay. All right. Now, right, we can use some logic or we can use some math. Okay. I'll show you both ways. Okay. So for the gazelle, right? This gazelle travels 1 kilometer, but his speed is 100 kilometers per hour. All right. So there's 2 ways we can do this. Jack, do you want to go out there, or you want to join us? Go ahead. So let's do the math part, all right? So here is our relationship for speed, right? Distance over time. This column is asking us to solve for what? Time, right? So we have to get time by itself, okay? So let's do some algebra and get time by itself, okay? First, it's in the bottom of the fraction. We don't want that, okay? So we can get it out of the bottom of the fraction one of 2 ways, okay? And how you do this is math and your brain and everything like that, and I don't care how you do it as long as you get the right answer, okay? So there's 2 ways we can do it. First, we can multiply the right-hand side of the equation by t, okay? But if we multiply the left or right-hand side of the equation by t, what do we have to do? Got to multiply the left side by t, right? An equation has to stay the same. So if we do something to one side, we have to do that same thing to the other side, right? So here, t's cancel, and we're left with t times s equals d, right? But we don't want that. What are we trying to solve for here? Trying to solve for t, right? So what are we going to do? We're going to divide this side of the equation by s, right? But if we divide that side of the equation by s, what do we have to do? Divide the other side by s, right? These s's cancel, and we're left with t is equal to d over s. Oh. Okay? Good there? All we did was just manipulate that equation algebraically, right? It's still the same equation, just solving for a different thing, right? So now we plug in our numbers, right? And what are we going to end up with as far as our time is concerned? One kilometer over 100 kilometers per hour, right? So we have 1 over 100, right? Equivalent decimal. What's the equivalent decimal of 1 over 100? All right, 0.01. Okay. What's the only time unit that's in that problem, though? Right. That time unit is hours in this problem, right? Does that make sense? You okay with that? So close. All right. So for the turtle tells us that the turtle goes 1 centimeters per second for 30 seconds. So hopefully, logically, we can go through and figure out that what's the distance that it's going to have to go. If it's going to go 1 centimeter per second for 30 seconds. 30 centimeters, right? Now, just like we did before, real quick, right? If that's our relationship, right? The turtle row asks us to solve for what in this relationship? Distance, right? So we can rearrange that equation to look like that, yes? Does that make sense what I just did right there? Okay, and that would give us distance 2, and we'd find out this is the same answer. Okay? All right, good there. Constant velocity, we okay with that? All right. But constant velocity, as we can tell from this chart and from this picture of the ball rolling along the floor, it's pretty easy, right? Why? Because what's not happening? Well, changing direction, or well, that means we could if it's not accelerating, it's not changing direction, or speeding up, or slowing down. None of those things are happening, right? Just staying the same the entire time. And that makes analyzing it pretty easy. But that's not what happens in the real world, right? For example, here, is a picture of a drag racer. Okay? And you can see here, it's showing us the position of the drag racer at consecutive intervals of time. 1 second after the start, 2 seconds after the start, 3 seconds after the start. Did you really think you were going to kick the ball? Okay. No. So, what are you seeing about the displacement of this drag racer in consecutive seconds? What's happening to the displacement of this drag racer as the seconds keep going? It's getting larger, right? It's farther away from its previous position each consecutive time frame. If the displacement keeps increasing, but the time interval is staying the same, what's happening to the velocity? It's getting bigger. Does that make sense? Right? So, how would we describe this motion? It says up at the top that it's accelerated motion, but we could probably be a little bit more descriptive than that. What type of acceleration is occurring here?
Speeding up.
Speeding up. We said that it could also go by what name? If it's speeding up, we could also call that what?
Acceleration.
What kind of acceleration?
Oh.
Well, let's do this. How do we define acceleration?
The rate at which velocity.
The rate at which velocity changes. All right, that's good. Mathematically, how do we define acceleration? How do we represent the rate at which velocity changes mathematically? Meters per second squared. Let's go with some variables first, though. All right. Delta V over T. Okay. We said the delta always represents what? Change, right? And to know the change in something, we need to know two things. What two things?
Initial.
And final, right? So we can write this equation like this as well, right? That's all the same equation up at the top, just becoming more detailed, okay? In this case, what did we say is physically happening to the velocity? It's increasing. So how does V final compare to V initial? In any case, no matter where we're looking at it along this path. How is V final compared to V initial? It's larger. So if we plug a larger number in for V final and a smaller number in for V initial, what sign are we going to end up with? Positive. So in this case here, because this object is speeding up, we could also refer to this as what? Positive acceleration. Oh, no. Sometimes my pen. I'm too fast for it. Positive acceleration. Okay? Good there. You okay with that? All right. Let's look at this guy and his bike. Okay? So, a similar situation to the drag racer that we just looked at, right? From this picture and where this guy is, this is like a time-lapse photo. It's showing where he is at 1 second intervals, right? This was the very, very beginning of his ride. That's why it was t equals 0 seconds. 1 second later, 1 second after that, 1 second after that. Okay? And you can tell from the pictures what's happening to his velocity. It's increasing, yeah.
This is less than 2 meters per second.
Hold on 1 second with that, all right? Hold on, okay? Because that's where we're going with this, okay? That's why we started with the constant velocity, and now we're going to this, okay? So, his velocity is increasing, all right? So, Jack, At 1 second, it tells us that he's going 2 meters per second, which is confusing you. Why? It says he's only at the 1 meter mark. That's a good thing to be confused about. In the picture before, right, we went 1 meter, it took 1 second, velocity is 1 meter per second. But remember, what's different about that picture versus this picture? The first picture we did today, what was true about that motion? It was what? It was constant velocity, never changing, exactly the same the whole time. But here, although he's going 2 meters per second right now, was he doing that the entire time? He had to gradually build up to 2 meters per second. He's going 2 meters per second now, but he wasn't doing that the entire time. Okay? So I'm going to throw a new term at you guys. Okay? This 2 meters per second, actually, you know what? I'm going to use a different color for my visual learners out there. Okay? Okay? So 2 meters per second would be the bicycle rider's instantaneous velocity. If we refer to something as instantaneous, what does that mean? At that moment in time. No other moments in time, at that moment in time. Okay? So Jack, yes, he's going 2 meters per second now, but that's not what he was doing the entire time. Okay? All right, now let's start building this into our discussion for tomorrow. Okay? Zara, you told us that acceleration is defined as what? How do we calculate the acceleration of something? Delta V over T. Right? So let's look at this little interval right here, from the bicycle rider starting here to ending here. Okay? First, is he accelerating during that time? Yes. What did his velocity start off as? 0. What is it now? 2 meters per second. How much did his velocity change during this interval? 2 meters per second. It went from 0 to 2. Does that make sense? So the change in velocity was 2 meters per second. How long did that change take? 1 second. So what is this bicycle rider's acceleration value? 2 meters per second, or 2 meters per second squared. All right? I'm going to say it as 2 meters per second to be more descriptive as far as what we're doing. Okay? Are we okay with that that's his acceleration during that time? Okay? All right. Color change. From here to here. Okay? So, 2 meters per second was his instantaneous velocity at this picture point. But what's his instantaneous velocity at the next picture point? 4 meters per second. Different instantaneous velocity, because that's the instantaneous velocity at that moment. Okay? During the green interval, how much did the velocity change? It changed by 2, right? During that green interval, he was going 2 meters per second at the beginning of it, but he's continuously going faster and faster and faster, right? And so his velocity changed by 2 meters per second. How long did that take? 1 second. So what was his acceleration value during the green interval? 2 meters per second per second. Good there? Purple. Right? How much does the velocity change during the purple interval? It goes up by 2. Does everyone see that? Right? The instantaneous velocity at the end of this interval is 6. It was 4. So it went up by 2. So delta V is 2 meters per second. How long did that change take? 1 second. What was the acceleration during the purple interval? 2 meters per second per second. This is an example of what, Frank? Constant acceleration. The velocity keeps going up by 2 meters per second for every second that goes by. Okay? So here, this is an example of accelerated motion, but more specifically, it's constant acceleration. Does that make sense? You okay with that? All right. You know what? That's a good place for us to end today. All right? We will talk about objects rolling down a hill tomorrow. We'll talk about gravity on Thursday. All right? Good there? All right. Oh, hold on 1 second. Freeze. You have lots of time, so you won't be late. Hold on. Freeze. So, this week, if you look at the calendar, there are no assignments for homework. Okay? Because this kind of stuff doesn't show up in the book. But it's important for our understanding of these concepts. So I really, really, really encourage you to look over the stuff that we do in class each night just to refresh your memory, and then tomorrow we come back and we're ready to go for the next thing. We can build on what we did previously. All right?
Yeah.
All right, see you tomorrow.
Peace out.